Hello friends, I welcome you in lecture number 48 on Laplace transform. In lecture number 47, we have discussed about second shifting theorem. In this lecture, we will discuss alternative form of second shifting theorem, which is useful in finding the Laplace transform of a given function. So first we recall the second shifting theorem, which we have discussed in previous lecture number 47. So if you have not seen that lecture, I suggest you to watch lecture number 47 first and then go for this lecture. So we recall second shifting theorem. It says that suppose Laplace transform of f of t is capital F of s, then Laplace transform of the function f of t minus a u of t minus a, this is equal to e raised to minus as times capital F of s. So if we are interested in the Laplace transform of this type of product of f of t minus a and u of t minus a, then first we will replace t minus a by t in this f of t minus a. So if I replace t minus a by t, I will obtain f of t. Then I have to find out Laplace transform of f of t, and I will multiply that Laplace transform by e to the power minus as. This is second shifting theorem. Here we will discuss another form of second shifting theorem. Instead of f of t minus a, suppose you have f of t in the product. Then how to find out Laplace transform? So that is also ready-made formula. Suppose we are interested in the Laplace transform of f of t multiplied with unit step function u of t minus a, then this is given by e raised to minus as times Laplace transform of f of t plus a. In this f of t, we replace t by t plus a and we find out Laplace transform of f of t plus a, and we multiply it by e raised to minus as. So in this lecture we will discuss examples of Laplace transforms in which we can use this formula. So remember this formula: if we have this type of function f of t times u of t minus a, then we will replace t by t plus a in f of t, and we will find out Laplace transform of f of t plus a, and that we will multiply with e raised to minus as. So we understand this with the help of these three functions which are in that form. So first function we have given is t square times u of t minus 3. T square times u of t minus 3, and we will keep in mind this formula: Laplace transform of f of t u of t minus a, this is equal to e raised to minus as times Laplace transform of f of t plus a. So if we compare this function with f of t times u of t minus a, we can see that value of a is 3 here, and f of t is equal to t square. So using this formula, Laplace transform of t square times u of t minus 3 equal to value of a is 3. So here we put a equal to 3, e raised to minus 3s, into Laplace transform of f of t plus a. Here f of t is equal to t square and value of a is 3. So in this function we will replace t by t plus a, that is t plus 3. So our function f of t is t square. In that function we replace t by t plus 3, and then we require Laplace transform of square of t plus 3. So this is the way how this formula works. So this is equal to e raised to minus 3s. To obtain Laplace transform, we have to expand this. square of t plus 3 is t square plus 2 into 3 into t, that is 6 times t plus 9. And we know how to find out Laplace transform of this function. For that we will use this formula, Laplace transform of t raised to n, and if n is natural number, is given by n factorial divided by s to the power n plus 1. So using this formula and linearity property, we obtain this is equal to Laplace transform of t square, which is 2 factorial divided by s raised to 2 plus 1, that is 3, plus 6 Laplace transform of t, that is n equal to 1. So we have n factorial divided by s raised to 1 plus 1, plus 9 into Laplace transform of 1, which is 1 by s. So here we have applied linearity property as well as this formula, and now we rewrite all these things. 2 factorial is 2 into 1, 2 upon s cube, 1 factorial is 1, so this I write as 6 divided by s square plus 9 divided by s. So in this way this alternative formula is helpful if our function is not given in this form. Second shifting theorem is given for Laplace transform of a function which is written in this form, but this alternative form is applicable if you are not given f of t minus a. If instead of f of t minus a, if you are given f of t only, then also you can use this alternative form of second shifting theorem. Second function is e raised to minus 3t times u of t minus 2. So we now consider second function, e raised to minus 3t times, let me check again, e raised to minus 3t u of t minus 2, e raised to minus 3t u of t minus 2. So first we compare this with f of t times u of t minus a, and we find that value of a is 2, f of t is e raised to minus 3t, and because a is equal to 2, we will require f of t plus a, that is f of t plus 2, that is nothing but e raised to minus 3 times t plus 2. We replace t by t plus 2 here. So this is just for understanding. You can directly write Laplace transform without considering these notations f of t and a equal to 2. That is for understanding. Otherwise you can directly write this using alternative form of second shifting theorem. If we compare, we find that value of a is 2. So here we will write e raised to minus as, a equal to 2, into Laplace transform of f of t plus 2. F of t is e raised to minus 3t, and in this f of t we have to replace t by t plus a. Value of a is 2 here, so we write e raised to minus 3 times t plus 2, and in the bracket we can simply mention that this is using second shifting theorem, okay, or by second shifting theorem. This is equal to e raised to minus 2s Laplace transform of e raised to minus 3t minus 3 into 2, that is 6. So this we can rewrite as e raised to minus 2s Laplace transform of e raised to minus 3t into e raised to minus 6. E raised to minus 6 is constant, so we can take it outside using linearity property, and Laplace transform of e raised to minus 3t, and this we can rewrite as e raised to minus 2s minus 6. Laplace transform of exponential function is s minus coefficient of t, which is minus 3, and finally we obtain our Laplace transform as e raised to minus 2s minus 6 divided by s plus 3. So this is Laplace transform of second function. These two questions were asked in GTU Winter 2019 and GTU Summer 2012 exam, and in all these cases we are applying this result. Laplace transform of f of t u of t minus a equal to e raised to minus as times Laplace transform of f of t plus a. Third function is cos t times u of t minus pi. So now we find out Laplace transform of cos t multiplied with unit step function at pi u of t minus pi. So this directly we can write as e raised to minus as, value of a is pi, into Laplace transform of this function in which we replace t by t plus pi. So here we write cosine of t plus pi. So here also we can compare. If you cannot understand directly, you can compare your function with f of t into u of t minus a, and you will find that f of t is cos t and value of a is pi, and we have to replace t by t plus a in f of t. So here we have cos of t plus a and value of a is pi, therefore we have cosine of t plus pi. Now cosine of t plus pi means we are in third quadrant. Up to this angle is pi, and t plus pi means we are having angle somewhere here. Suppose this is t plus pi. So we are in third quadrant, and we know that in third quadrant tan function is positive, sine and cosine are negative. So this I can rewrite as minus cos of t, and we know Laplace transform of cosine function, negative sign outside, cos t has Laplace transform s divided by s square plus 1 square. So finally Laplace transform is minus s e raised to minus pi s divided by s square plus 1. So this is the alternative form of second shifting theorem, and using this form we can easily obtain Laplace transform of a function which is in this form, or which we can express in this form. If we can write our function in this form, f of t times unit step function at a, then Laplace transform of f of t into u of t minus a is given by e raised to minus as times Laplace transform of f of t plus a. In f of t we replace t by t plus a, and we find out Laplace transform of f of t plus a, and we multiply it by e raised to minus as. So remember this alternative form of second shifting theorem also, it is very useful. So this is all about this session. I hope you like it. Thank you very much.